lecture, we will continue about the microstructural models for bitumen. In the previous two lectures, we had discussed about the different scales of characterization and what are the other characterization aspects that have been used on bitumen. So, in this lecture, we will focus on the microstructural models and what is the relation between the chemical composition and physical properties of bitumen. So, when we look at the microstructural model, bitumen was modeled as a colloid as early as 1924. In 1924, Nellenstein proposed a first colloidal model. So, what do I mean by a colloid? We have two materials, one is dispersed in another. So, we have one component which is dispersed and another one which forms a matrix. So, we can represent it something like this. Right. So, we have some particles which are dispersed in something else. So, this was the initial colloidal model which was proposed in 1924 by Nellenstein. So, here this particle which is dispersed was called as asphaltenes. One which forms the matrix is called as maltin. So, there are two components, the dispersed phase is called as asphaltenes and the matrix which is the medium in which these asphaltenes are dispersed is called as maltin. Later, Pfeffer and Saul worked extensively on this colloidal model and they proposed a hypothetical structure considering different fractions of bitumen. So, here they have different fractions, let us look at one by one. The filled black one, right, what we see here, this forms the central part of asphaltenes, right. So, this is the asphaltene agglomerated together which forms the central core and these one are surrounded by compounds of high molecular weight and aromatic nature. So, we see this one here, right, I will show you here. So, there is a hexagon which is having a dark outline. So, these are compounds of high molecular weight and aromatic nature. So, we have a central core of asphaltene surrounded by high molecular weight compound. Then we have compounds of lower molecular weight and predominantly aromatic in nature. So, we have something here, we show a hexagon here with a lighter outline. So, these are lower molecular weight but aromatic in nature and we have these circles here which are compounds of mixed aromatic and naphthenic nature. So, which means that they are aromatic and they also have cyclics. Then we have this line which is shown here, compounds of mixed naphthenic and aliphatic. So, previously we had aromatic and naphthenic, now we have naphthenic and aliphatic nature and these straight lines are compounds of aliphatic in nature. So, when we see the molecular weight and the size of these molecules keeps decreasing as we move from this center of the core to outer space. And they also said there is no significant boundary, you cannot say this is a particular thing which forms, this is called as a missile, right. So, this is referred to as a missile and this is there in the dispersed medium. So, this one which is present here is called as an asphaltene missile, right. It is called as an asphaltene missile and this is dispersed in a medium. So, in this paper the Pfeffer and Saul have proposed that there is no clear cut boundary between this asphaltene missile and the matrix in which bitumen is present. So, they say there are missils which are present, the central core formed by asphaltene and the molecular weight keeps decreasing as we move away from the central core, but there is no clear cut boundary when this missile ends and when this matrix starts. So, this is the model by Pfeffer and Saul and they use this model to explain a sol and a gel bitumen. We will first start with a gel bitumen. We can see in this gel bitumen, we have all these missils which are closely packed to each other, right. So, they have some strong attractive force between them and they are closely packed in this case. But we have a sol bitumen wherein they are not as closely packed as in the case of a gel bitumen. These missils are spaced apart from each other. So, bitumen, any given bitumen can be of a salt type or of a gel type. So, a gel bitumen generally has a higher viscosity value compared to a sol bitumen. But we should remember here that a given type of bitumen can exhibit both gel behavior and sol behavior depending upon the temperature. At low temperatures, we can say that the microstructure of bitumen will exhibit something like that of a gel bitumen, whereas when we move to high temperatures, this microstructure will exhibit something like as a sol bitumen. So, either a given bitumen can have either of these two behavior, or two types of bitumen can have either of these two microstructure. So, these were two types of models which were proposed by Pfeffer and Saul, and this is extensively used to explain the temperature dependent properties of bitumen. Then people proposed a model which is called as an SHRP model, because in the previous model by Pfeffer and Saul, they did not focus on the interaction which exhibits at different points in a given molecule. So, to capture these interactions, the SHRP model was proposed. So, this SHRP model considers interactions among different constituents. We said previously when we were talking about the fractionation technique, we have different fractions. The interaction among these fractions is very important. So, this SHRP model tried to focus on these interactions. They say the polar sites of bitumen are favorable sites for association of polar molecules through electrostatic forces or hydrogen bonding. So, previously when we were talking about heteroatoms, we said they are points through which the strong attractive forces will occur between different molecules. So, these attractive forces are because of electrostatic forces or hydrogen bonding, right. So, this is the basis on which SHRP model was built, and they also said it can have few other interactions such as pi-pi bonding of the aromatic rings. These aromatic rings undergo some kind of a pi bonding, and there is also van der Waals interaction of long chain hydrocarbons. So, these are few other interactions that were proposed as a result of this SHRP model, but then this SHRP model was not further expanded to add more details to these interactions. There is another model by N where they have proposed a structure for these asphaltenes. They have said that these asphaltene core forms the micelle, or these asphaltenes form the core of these micelle, and they try to say what is this micelle composed of. So, they say these asphaltenes have some kind of an arranged structure. So, they form a monomeric sheets, right. So, they form some kind of a sheet like structure, something like this, some orderliness in the amorphous fraction, and these monomeric sheets join together to form different types of micelles. You can see what is the size of these monomeric sheets from 1.5 to 2 nanometer, and they join together to form micelles which are 2.5 to 5 nanometer. Now, these micelles join together to form a super micelle which is of 10 to 20 nanometer. So, we have different micelles joined together to form a super micelle which forms a giant super micelle, or it can also form a multi-lamellar vesicle. So, they can either be arranged in form of a sheet, or they can take the form of a micelle which is in the form of a globule. So, then they join together to form a flock, or in other case they can join to form a liquid crystal or a gel. So, that is what they also say, it can be either present in a gel state, or it can be present as a flock in a sol state also. So, this is the hypothesis which they have proposed in relation to the asphaltene molecule, and they also did some microscopic studies to identify the sizes of each of these micelles. So, these are some of the colloidal models which are available today, but still the colloidal model which was proposed by Nellenstein and further expanded by Pfeffer and Saul is currently used. So, this colloidal model is preferred to describe the microstructure even today, and in the year 2013, Lukanen et al. Used this colloidal model to explain the temperature dependent properties and aging of bitumen. So, they say that there is an asphaltene core which is present in bitumen. This is further surrounded by the resins fraction, and they also use this to calculate the effective volume of the cluster. So, these are some of the atoms which are made in this regard, expanding on the colloidal model. It is used to explain the temperature dependent and aging properties of bitumen. So, we will discuss more in detail about these factors when we talk on aging of bitumen. Next, we move on to the relation between chemical composition and rheological properties of bitumen. So, ultimately we understand that the chemical composition is what is influencing how a material behaves. So, we need to understand how the chemical composition influences each of the rheological properties of bitumen. So, why do we need to understand this? So, we have some particular property of bitumen, say for example moisture damage. We need to reduce the moisture damage in bitumen. So, then we need to make this bitumen have more affinity towards the aggregates, and when moisture interferes this system, it should not rip away this bitumen from the aggregates very easily. So, for that purpose we need to ensure a strong bonding between bitumen and the aggregates. So, for this purpose people have said that specific functionalities in bitumen can improve the interaction between the aggregates and bitumen and reduce stripping. So, one such functionality is amines. The presence of amines can improve the bonding between aggregates and bitumen and reduce stripping. So, if we have a bitumen with more amount of amines which is present in it, then we can say that it will reduce the stripping properties. So, if we have some links between the chemical composition and rheological properties, then we will be able to say or tweak the chemical composition of bitumen to obtain the rheological properties that we desire. Or in general we can say that we will be able to design bitumen with specific requirements. But still this is not a very simple task, it has lot of steps involved in it and it is very complicated. We will understand what leads to its complexity. So, this is an image given by Peterson et al. Where they have tried to relate the asphalt chemistry to its field performance. So, we understand that asphalt chemistry focuses on the chemical composition of bitumen. So, for many other polymers we can say that this is the structure of this particular polymer, this is the manner in which each of these molecules in this material is arranged, and so it will lead to this kind of a performance. So, when we want to predict the performance, they derive models from its microstructure. They say that if this microstructure is behaving in this manner, it will lead to this kind of a rheological response. So, such correlations are possible for simple polymers, but for bitumen it is very difficult to arrive at such correlations, because we know the variability that is induced in the material because of the crude source processing methodology, and it also exhibits a viscoelastic behavior. So, we have to quantify what is the effect of different parameters like time, temperature and all the other variables on this behavior, and finally we have to relate it to the field performance. Again, field performance, each and every location is subjected to different environmental conditions. The effect of temperature, rainfall and the availability of oxygen, the properties of mixture are number of variables which will affect the behavior of binder. So, even if we have two binders and we want to compare its performance, depending upon the location where the binder is used, its performance is going to be different. So, correlation between chemical composition, its rheological properties is the first step, then rheological properties to field performance is the second step. We also have a small step here which is the mixture properties. So, establishing this big link is very complicated as far as bitumen is concerned. So, people say that we have asphalt chemistry. So, based on that chemistry, we try to propose a microstructural model, right? Model to describe the microstructure of bitumen. Based on the microstructural model, we have to propose a rheological model. And from the rheological model, we will be able to arrive at specification criteria, because ultimately the binder is going to be used in field, and whatever is the specification requirement, we will be able to tweak it depending upon the variability in asphalt chemistry and the microstructure. So, this rheological model will result in specification criteria, and using the specification criteria, we will be able to specify mixture properties, and from mixture properties the field performance, right. So, we have a big link here and we have a number of steps here. So ultimately the interest is to correlate the asphalt chemistry to field performance. So lot of attempts are being carried out in this regard, but we need to understand the variability associated in each of this step in the process. Let us now see what are the attempts in this regard. The foremost attempt is to correlate viscosity to asphaltene, because we said the asphaltene fraction is of high molecular weight, and when they aggregate or agglomerate together, they tend to increase the viscosity of the system. So people propose that the amount of asphaltene content which is present in bitumen can directly influence viscosity. Then later a number of studies tried to verify this fact. So we can see in this regard, we have asphaltene content on the x axis and we have viscosity on the y axis. So we can see that depending upon the type of bitumen, again this is 3 different type of bitumen with different proportions of pitch and extract. So from the lecture on the refinery processing, by this time you will know what a pitch is, what an extract is. So this pitch and extract were combined in different proportions. So in one case 75% of pitch and 25% of extract, in another case 90% of pitch and 10% of extract, and in the third case 85% of pitch and 15% of extract. So they were combined in different proportions to get bitumen of different grades. So we can see in each of them the increase in asphaltenes reflected in an increase in viscosity of the system. However, the slopes were different depending upon the proportion of pitch and extract, but still we can see that there is almost a linear relation between increase in asphaltene content and increase in viscosity. Sometimes people have observed that this linearity can be piecewise linear, which means that it can have one particular slope up to a specific concentration of asphaltene and a different slope for another range of concentration of asphaltene. But this viscosity and asphaltene relation was strongly established. Then people started looking at the carbide fractions and they tried to see if this variation in carbide fraction or if the magnitude of this carbide fraction can be related to the physical properties of bitumen. So they have taken 2 different type of bitumen. One is an Boscan AC20 and the other one is a California Valley AC20. So 2 different type of bitumen, and we can see the composition. The saturates plus aromatics combined together, the polar aromatics and asphaltenes were almost identical in these 2 type of bitumen. So from the carbide fractions perspective, they both can be considered as identical bitumen. But when we look at the physical properties, we can see how they vary. We will start with penetration. So we should mind that the units are given in degree Fahrenheit. So when we look at penetration at 39.2 degree Fahrenheit, we see that the Boscan AC20 has a higher penetration value compared to California Valley AC20. So this one is a softer material compared to the other one at 39.2 degree Fahrenheit. Next, when we move on to penetration at 77 degree Fahrenheit, again we can see that this material has more penetration value, indicating that it is a softer material compared to the other case. Now when we see viscosity, we also see this viscosity at 140 degree Fahrenheit. Again we can see that this California Valley AC20 has higher viscosity, which means that it is a stiffer material again at 140 degree Fahrenheit compared to Boscan AC20. Similarly is the softening point and ductility at 60 degree Fahrenheit. So we can see that the asphaltene fraction, the carbide fractions are same in both the materials, but we see that their physical properties are completely different. So as we defined earlier, it is not the magnitude of the carbide fractions alone, but how they interact with each other is also going to influence the physical properties in a significant manner. Next we will move on to another attempt where they tried to correlate the performance grade properties of bitumen to its elemental composition and the functionalities that are present in bitumen. So this was the study which was conducted by Pieri et al. So there they had taken bitumen from different sources. So we can see AAD1, AAO, AAM1, So, these are bitumen from different sources classified under these names by SHRP. Right. So, we have different types of bitumen. They try to establish a correlation between certain indices calculated from FTIR spectroscopy. Right. So, what are these indices are? You have some amount of this functionality present, you normalize it, and that we call it as FTIR index, and that is correlated to the rheological properties of bitumen. We will use some parameters which we have learnt in performance grading for this purpose. They have taken G star by sin delta. We know that this G star by sin delta is used to represent the rutting properties of bitumen. Similarly, stiffness at minus 10 degrees is used to represent the fatigue properties of bitumen. Right. So, they have used these two parameters to represent the rheological parameters, and a number of parameters are seen on the right hand side. Right. So, these all relate to the elemental composition and the functionalities. So, what this BA is? It is the branching index. So, it says how much of the aliphatics which are present in bitumen are in branched form. Similarly, this FA is factor of aliphaticity, which says how much of the composition in bitumen are present in aliphatic form. Similarly, 3 substituted aromatics, that is the aromatic structure with number of substitutions that are present. This we say is the vanadium content that is present in bitumen. So, they were able to obtain a correlation between the G star by sin delta and a regression equation arrived using these 4 parameters. You can see, using this regression equation, they predicted the G star by sin delta, they measured this G star by sin delta using a rheometer, and they were able to get positive correlation. Similarly, they also explained the stiffness at minus 10 degrees Celsius using another regression equation with a different set of parameters. So, such correlation between the rheological parameters and the chemical composition was possible, but most of them are regression equations in nature. They are not fundamental equations explaining the microstructure of bitumen. Next, we will move on to another attempt which tried to capture the solid-solid transition in bitumen. So, what is this transition in bitumen? We know that bitumen exhibits a wide range of behavior, right. So, it starts from the elastic solid at one end to a viscoelastic fluid or a Newtonian fluid at another end. So, there is a wide range of behavior exhibited by bitumen. In the working temperature range, it exhibits a viscoelastic response. Again, we know that the viscoelastic response can be subclassified. It can be called as a viscoelastic solid like or a viscoelastic fluid like. So, you know all these basics and what each of them mean. So, then there was a study which was conducted to find out when the transition between the viscoelastic solid like and the viscoelastic fluid like occurs in bitumen. So, this was measured at 2 different length scales. One is using a rheological test, a temperature sweep test. So, again you know what a temperature sweep test is. The torque was measured from this temperature sweep test and a torque derivative was calculated with temperature. So, this torque derivative was observed, and at 57 degrees Celsius some transition in the material was indicated by this parameter. Similarly, the FTIR spectroscopy was done at different temperatures, both of them in the same temperature range from 25 to 75 degrees Celsius. It was done for different set of binders. Again, here we can see in the temperature range between 45 to 65 degrees Celsius, depending upon the type of bitumen, we were able to see some transition in the material. So, these are an unmodified, elastomer modified, plastomer modified and crumb rubber modified bitumen. I will not get into the details as they get more research oriented. So, I will just stop with this attempt where they have used techniques at 2 different length scales to quantify a particular aspect of this material, and we are able to get some identical correspondence between these 2 different scales of measurement. Next, we will move on to another study wherein the influence of production process was quantified. So, we know that we have bitumen from 2 different processes in India. One is blended, or which is called as component blending. The other one is air rectified or air blowing, it is partial air blowing. Alright, so these are two different techniques which are commonly used in India. So bitumen of a particular grade was obtained from each of these two different processes. When we look at the stress relaxation behavior of these two types of material, we can see that the stress relaxation behavior is completely different for a blended material compared to an air rectified material. Though they fall under the same grade, they behave differently. This is what I mentioned when I initially started this lecture on chemical composition of bitumen. To understand why two bitumen of the same grade behave in different manner, we need information on the chemical composition. So for that, FTIR spectroscopy was performed and the carbonyl index was calculated in unaged, short-term aged and long-term aged condition. Again, this stress relaxation corresponds to long-term aged condition. So in the long-term aged condition, it was seen that the blended bitumen has more carbonyl index compared to the air rectified bitumen. So what this carbonyl index is, what it means, we will discuss when we talk about aging. But there is some parameter which can quantify aging. So it was seen that how this material ages is completely different, and there is a correlation between carbonyl index and stiffness of the material. Higher the carbonyl index, it is generally said to increase the stiffness of the material for most cases. So this blended material has more amount of carbonyl index, and that was the reason for the increased stiffness in the stress relaxation test that was observed. So again here we can reason out why two bitumen behave in different manner by studying the chemical composition. So these are some of the atoms which were carried out to correlate chemical composition and rheology. Again, it is not a very simple task. We need to understand the lot of variability that is associated in this process. Now we will summarize what we have learnt in this topic on chemical composition of bitumen. So like I mentioned earlier, bitumen is not a designed material. We have not designed bitumen specifically for paving purposes. It is the end product which is obtained from the refinery processing. We have taken this material and we have tweaked it for paving purposes. So there is complexity in its chemical composition because of the crude source and the processing methodology. So this complexity makes the characterization challenging. And we also saw that it is not possible to associate specific structures to this material. We said we can identify the elements which are present in material, but it is not possible to identify and define the molecules which are present in this material. So that is why we are using some fractionation techniques. Again, depending upon the requirement, we have to use appropriate techniques. So initially we saw characterization at an elemental scale, then at a molecular scale, then finally at a fractionation level. So depending upon what is the application that is required for bitumen, we have to use different techniques. So these are few of the techniques which are used for bitumen. For aging, we saw that we have to identify functionalities in bitumen, so we will be using FTIR spectroscopy. For modified bitumen, we saw morphology related techniques were very successful. So for modification purposes, we are going to use morphology related techniques. For information on crude source and production process, we can use FTIR spectroscopy to quantify the changes at the microstructural level, and we can also use solubility based techniques which are nothing but the fractionation procedures. And to identify transitions which happen in this material, it has to be evaluated at different scales. The rheological property to show when transition occurs and the microstructure related techniques to show why this transition occurs. So we have a combination of rheology, DSC which is nothing but differential scanning calorimetry, and FTIR spectroscopy. So ultimately we want to relate performance to the chemical composition of bitumen. So for this purpose we need some hypothesis. What do we mean by hypothesis here? We need to say that bitumen behaves in this particular manner and we need to choose an appropriate technique to verify that hypothesis. So initially people spoke that these elemental composition and the functionalities have some relation to the rheological properties of bitumen. So if we see the study by Perry et al. Which we discussed, they have functionalities on one end, and they thought that it is going to influence the rheological properties. So, they chose a parameter G star by sin delta to capture the rheological parameters. They chose few functionalities and heteroatoms, then they tried to make a correlation. So, this correlation between chemical composition and rheological performance has to be made with some hypothesis and choosing appropriate technique to verify the hypothesis. Finally, colloidal models, though we know its limitations, are still preferred to represent the microstructure of bitumen. So, it helps to motivate discussion as they form a hypothesis, and we can verify what this hypothesis says for bitumen. So, with this we will wind up our discussion on the chemical composition of bitumen. I thank you for your time here.